processes, particularly flow in rivers. So this system is like a small laboratory section of a river, and it's got a sediment bed where the sediment, the sand, can actually move under flow, and then it's got this overlying flow that gives you the equivalent of a little piece, and the water is continuously recirculated through a pipe, so you can run this indefinitely. We use something similar to this to do experiments on things like river flow processes, on fine particle transport, sediment transport, carbon, nutrients, pathogens, contaminants, wide range of things. And there's actually a lot of interest in that right now because, generally speaking, we don't understand very well how environmental interfaces perform. So like the river subsurface interface, we don't really understand how contaminants migrate across there, and how contaminants and sediments are released, and how organisms grow in this environment. So we set this up to do just a basic flow demo, and we're going to do some flow visualizations. You don't want to stand here, you can't see. So I just have some dye, right? So this is just red food coloring, and we can inject it, and then you can see how complex the flow pattern is. So first of all, the river flow generally is turbulent. So you guys know what turbulence is? So what's that? So yeah, it's kind of a chaotic motion. So you'll see a lot of eddies. So if you look over like a big bridge, you can often see these huge eddies. So even at this relatively small scale, and it looks like a very smooth flow, it's really not.
Excuse me, really quick, is it okay if we take pictures and video in here?
Sure. No problem. You can find a bunch of photos and videos of this kind of stuff on our website. Anyway. So if I just drop, little drops, you want to be able to see, right? So you can see the flow, and if you look at them closely, you can see that they spread out in a very complicated fashion. Probably back there you won't see too much, but you should really use the back room. So this corner is the worst for viewing. So if I put, in fact, maybe it'll be easier if I put this in here and I do this injection, you can see that it's really a complicated flow pattern, and the dye doesn't spread out uniformly. I mean, it does spread out, but it goes all the way to the edges, and it goes vertically quite a bit. So you can see, just doing these simple dye injections, you can visualize the turbulent flow, and you see that it's a really complex flow pattern. And in fact, this complex flow pattern over the sand produces these shapes. So if you go to a nice clear sandbed river, you would see things like this. So do you know what these are called, or what do they look like? So they're called dunes. So generally speaking, this series of shapes you would find, this roughness on the bottom of the river, are called bed forms, because it's the stream bed and there's forms on the bed. But this particular shape is called dunes, and they form really commonly under just a flow that's continuous in one direction. And basically what happens, that sediment is picked up on the upstream side and piles up, and then it just avalanches on the downstream side. And it forms naturally like this in this series of features. So the flow interacts with that quite a lot. So, so if you see here on the downstream side, there's this big circulation. You guys see that on both sides? This is because this turbulent flow, when it goes over the top, it can't follow that sharp crest, and the flow, it actually separates over the top. So if I can get it injected right in here, you should see that it goes right over the top, more or less. And some of it gets caught in this big eddy. So these eddies are common features of rivers. You find them over these dunes. This is exactly what we see like behind bridges, or if there's a big pool of water on the side of the river, you'll see this water kind of slowly going in and out of that. And that's really a complex flow field and hard to predict. So do you guys have any questions about that? Yes?
What did you say this will help you figure out?
So there's been a lot of interest in just this turbulent flows in rivers, because that defines a habitat. So any organisms that live in a river are subjected to that kind of variability that you see there. And one example where you see these eddies, things like fish, particularly like salmon swimming upstream, they have to go upstream in these really fast-flowing rivers. they'll find those little pools, those little recirculations, and they wait there, and they actually rest. So they'll swim upstream against that fast flow, find a little pool, rest there, and then keep going. So there's a lot of reasons why we are interested just in this flow process. But mainly what we do here is actually look at the interaction of the flow in the stream and in the sediment, right? So this looks all solid. This part. So this looks quite solid, but it's not, because this is all sand, right? So about a third of the space of the volume in that bed is water. So that's the porosity. And even though that water is trapped in there, it can move through the pore space. So what we're mainly interested in is how the flow in the surface in the river interacts with the flow in the subsurface. And that's really important for things like carrying contaminants back and forth, for releasing contaminants from contaminated sediments, like in the Fox River or the Hudson River. Do you know why those are important? So why is that? Do you know?
These dirty.
Yeah, do you know what's in them? There's Fox River and Hudson River are kind of the two big sites for a particular kind of contaminant. Did you know? So these, what's that?
I just knew that they were really contaminated.
Yeah, so they have PCB contamination in the sediments. So that's a solvent that was produced by General Electric and some other companies, and it's really persistent in the environment. So over a long period of time, the sediments of those rivers have gotten really loaded with this particular contaminant, and there's a lot of interest in how quickly it is being washed out of there, right? So if it's coming out really quickly, then you have exposure to organisms and people and potential health effects through fish consumption. And if it's being retained a long time, then maybe it's not a big concern, right? So we're interested in these issues of how water moves between the water column, the river part itself, and the subsurface. And it's actually moving now and continuously. So I can show you that by putting in lines of dye. I'll put them on close so you can see. So if I put in a line like this, what do you think is going to happen to that? So you would think it'll spread. So in fact, we distinguish between just a main flow, where things moving one direction, from spreading. So spreading in a sand bed occurs by a process called dispersion or diffusion. So basically, it's really complex structure in there, and the water flows many different directions, and it causes the dye to spread out over time. But in addition, it'll move, and it moves because over these dunes, there's a variation in pressure. So there's higher pressure on the upstream side, lower pressure on the downstream side, so it should move over time. Conversely, there are places it will move upstream. So it can do kind of not very obvious things. So in fact, because you have this series of dunes, and there's high pressure and then low pressure, high pressure and then low pressure, the water will flow from the high pressure locations to the low pressure, and in the subsurface, in the pore water, it can actually flow upstream, which nobody ever believes till they see it. So the thing is, you can tell it's very slow, because again, if I compare it to the dye flow in the river, you can see that this goes much faster. It's probably 10 centimeters a second. This pore water flow is usually quite a bit slower, so something like centimeters per minute or centimeters per hour. So we'll have to wait and see a little bit longer how that changes shape. Has it changed at all yet? It's moved. So the other thing that's interesting, okay, you can see it's moving here too. So can you see where it's moved at all? So where? So it moves downstream, but I made a vertical line, right? So it should move more at the top, though it's not guaranteed, right? Is that what you see here? Does this move? I can't really see from this. But it hasn't really moved down at the bottom. Right. So this is because this pressure variation occurs at the surface of the stream bed, and so the water that's in the pore space here will actually move faster. The closer it is to the surface. So these straight lines over time, they should become kind of curved because the water at the top is moving faster. And then you can see near the top it leaks out over time. Alright, so this is generally known as surface groundwater interactions, or in rivers in particular it's called hyporheic exchange. Does anybody know Greek? Probably not. Hyporheic comes from Greek. It's just two Greek words put together. It stands for beneath the flow, hyporheios. And it's a term that some stream ecologists came up with to describe this flow underneath the river. Right? So that's also very important for organisms that would live in the sediments in the pore space. Right? So habitat for things like mayflies, caddisflies, and a lot of other organisms. Alright, so there's a lot of kind of basic reasons why we want to understand these flow interactions for ecology, biogeochemistry, nutrients, carbon, and then also for engineering purposes like contamination or cleanup of contamination. So you guys have any questions about this part? Okay. So Antoine, you have some photos of this to show. So people that want to come up and look more closely at the flume here, you're